So we must start from, yes, we must start from the half. So let me spend some minutes to scan through the previous sessions. Okay, now let's go on. There are many generalizations of the Riemann-Roch theorem, like the Hirzebruch, which is in the analytic context, Hirzebruch Riemann-Roch. That is, we generalize to complex manifolds and also vector bundles. Then we must use many complex techniques, because we are treating with, when we're treating with complex manifolds, then we cannot then even if line bundles are corresponds to codimension 1 subvarieties. And vector bundles has more characteristic classes, because we have a total Chern class, which is C0, is C1 plus CR. So we have more more data involved, and we need to combine them together. So we need more complex techniques, complicated techniques, and also the more generalized version, the Grothendieck Riemann-Roch theorem, which is a relative version, which is something like a commutative diagram. And between the two subspaces of between algebraic varieties, or between the complex manifolds. So it is a commutative diagram that relates to cohomology theory. This is one type of generalization, but we use another different approach to this. That is, we only consider compared Riemann surfaces. And vector bundles. But we are considering with compared Riemann surfaces with boundary. And vector bundles, we are considering pairs of vector bundles. When we consider things with boundary, then vector bundles should have boundary data, like if we have e to x with boundary dx, then we must have we have a pair. And so we should expect a corresponding pair on the vector bundle, so that E is a vector bundle on X, and also F is a subbundle of E, and it is defined on dx, and it's a subbundle of E restricted to dx. In this case, X is complex, and we also require E to be complex, but the problem is that on the dx is not a complex manifold. It is in with obvious reasons because the dimension must be 1, not 2. So we just like the model is the half plane, is the upper half plane, and in this case we have a line on the we have a line as a boundary, and the interior is a complex manifold. So we know that it is complex and the line is real. And in this case, it is natural to associate to the boundary a totally real subbundle, like the trivial bundle. Like if the trivial bundle Cn, then we pick a subbundle Rn and we set this to be F, and this to be E. That is what we are considering here, a complex vector bundle E. And also a totally real subbundle F. And in this case, the topological indexes are the topological indices are relative with respect to the boundary. We know that when we have a Riemann surface with boundary, then the data is quite complicated. The data is totally different from the case without boundary, because like a Riemann surface X, if it is compact Riemann surface, then we know that X has a non-trivial homology group in H2, H2 X state, X state, which is served as a fundamental class. But if X is a compact Riemann surface with boundary, then we will have the second homology class X vanishes, but we have a corresponding relative one-dimensional homology class, and we set it to be the fundamental class. So in this case, we can even prove that the pair X and dx has a X is homotopy equivalent to a wedge sum of circles, where the circles where n is the number of boundary components. We know that for compact Riemann surface with boundary, the boundary should be a closed one-sum manifold of X. So, but we have a classification theorem for all one-dimensional manifolds. That is, it must be a circle or a line, or with boundary it must be so one-dimensional manifold must be circle, a line, a segment, or a ray. So in this case, we have it must be a closed one manifold, so it must be circle. And we have also a relative index for a bundle pair, which we will be discussed later, because it requires some work in homotopy groups to give the definition of such -1. Uh, uh, yes.
So I mean, if you think about it, it has one boundary that's homotopy to a point, right?
Yes, it should be -1. Yeah, yes. Okay. So the definition of this invariant is very important. It is called the Maslov index, or to say the boundary Maslov index. Or it is a forgot to say it is a relative first number of the bundle pair E and F. So I'm not going to okay. So that's a very rough introduction, and I'm not going to state this in the first 1.5 hours. So let's next let's give some yes, give some motivations of why we want to give such a generalization of Riemann-Roch theorem to the case with boundaries. This comes from flow of theory and also pseudo-homomorphic curves. Oh, I need to give some okay. Yes, if you are interested in the details of the proof, like the classical version or the set duality, you can refer to some context. And I have written in the notes, and yes, with links. It's Kerwan's complex algebraic curves, and they are very classical. They are very classical contexts. One is the Kerwan's complex algebraic curves, and the Shader Shader's introduction to characteristic class and index theory. Okay. So are there many questions? Are there any questions? So let's just move on. So I think I should give some basic concepts of symplectic geometry. The first one is symplectic manifold. So let X be a let X be a differentiable manifold of dimension 2n, and we let omega is how to write this? Oh, okay, just a global differential two form. So we say the pair X omega is a symplectic manifold. If we require the omega to be closed and non-degenerate. Okay, it is best time to go into the meeting because we are talking about symplectic geometry. That non-degenerate means that omega n is a volume form. No, it's everywhere non-vanishing. So we say such a thing is a symplectic manifold, and we say F from between a smooth map between two different symplectic manifolds is to be a symplectomorphism. If F pulls back omega y to omega x, and F is a diffeomorphism. Let me see how to moving on. There are many concepts to introduce so that we can reach the Arnold conjecture and to see how the pseudo-homomorphic curves went into symplectic geometry. So okay, symplectic, and we are concerning the deformations of symplectic structures. That is, if we have a phi t of x cross 0, 1 to y, a family of smooth of deep symplectomorphisms, is called symplectic isotopy. And we are mostly interested in the exact case, and in particular Hamiltonian case. Exact means that we have a corresponding vector field that is the derivative with respect to t, and we say it is exact if no, we say it is this should not exist. So we say it is Hamiltonian if xt comes from, or to say xt is a Hamiltonian vector field. Hamiltonian vector field means that since we know that omega is non-degenerate, or we say it is non-degenerate as a two form, that is school symmetry bilinear function. So we have a corresponding isomorphism from the dual of that is from tangent space x to the dual space Tx star. No, it is the tangent space Tpx to the dual space Tpx star, and this gives us a vector field xt, which satisfies omega. Plugging the xt is no. Let me. Yeah, Hamiltonian means that there is yes, omega gives an isomorphism from Tpx into Tpx star, and we say the vector field is Hamiltonian if there exists a function h that is a smooth function from x to r, and such that h the differential one form dh is given by the interior product of xt with omega. That is, we plug in xt and we must obtain dh, and this will give a smooth vector field. I think we must require h to be depend on time. So dht, d is with respect to the x. Yes. Okay. So like why Hamiltonian vector field is of most interest because they naturally arise in classical mechanics as energy functions. So in most cases, symplectic manifolds are recognized as phase spaces of classical mechanical systems. So we have a naturally associated Hamiltonian function h, and h will serve as a let me see how to express. Yeah, so h will serve as a deformation. Yeah, so this will give a Hamiltonian vector field is a solution to the Hamiltonian equation. No. The Hamiltonian. Okay. Let's just move on. So let L. So a submanifold of a symplectic manifold X is called Lagrangian. If for each P in L, TPL as a subspace of TPX, TP star of L is as a subspace of TP star of X, which is a symplectic space. Since we have associated a non-degenerate two-form omega, so it will be a symplectic space, and it's a Lagrangian. This means that omega restricted to TPL is identically 0, and TPL and the dimension of L is half of the dimension of X. So what we need is we don't need this. Okay. So Arnold conjecture concerns about the pair of a symplectic manifold and Lagrangian submanifold L. So we have if we have an exact symplectic isotopy, phi t. Here exact means Hamiltonian. An exact symplectic isotopy phi t such that phi t maps L to a. We know that if phi t is a symplectic isotopy, then phi t preserves the symplectic form. So it must map Lagrangian submanifolds to Lagrangian submanifolds. And in this symplectic deformation, we will have a corresponding image of a symplectic of the Lagrangian submanifold, and we make it to satisfy the condition that phi 1L and L are transversal. Do I need to explain the concept of transversal. This means that at each point of L, TPL and in the intersection, for any point in the intersection, the intersection of TPL and the TP of phi 1L is 0. This means that in fact they sum to no. This is the definition. TPL plus because they may not be a direct sum, but we must require that TPL plus TP of phi 1L must equal to the whole space TPX. So in this case, this means that TPL and TP phi 1L are direct summands of the tangent space of X. And also we have and also the set is a 0-dimensional submanifold of X, i.e. it is discrete. So in a case X is compact, phi 1L and in intersection of phi 1L and L, then the number of this set is finite. Then we can or we may wonder the intersection number lower bound of the intersection number. And another conjecture says that once we have X and L with X involutive, that is with an involution phi from X to itself with phi pullback omega to minus omega and phi square is 1. I square is identity. That is called an involution. Like in the classical case, like T star of a smooth manifold, and we just pick the canonical form d theta. We just pick any point PV to P minus V, then we get such an involution. And compact. So this may not serve as an explicit example. Another example is CPN with the Lagrangian submanifold RPN, and this will be involutive. And compact, then the lower bound satisfies. Then, or we say phi 1L intersect with L is greater than the sum of Betti numbers. With coefficients in a field. This is an Arnold conjecture, and Flower proves this in a special case. That is, this is true if X is compact. If we have a topological restriction and not require X to be involutive. And also a special case of this is the Hamiltonian version. So this requires a Hamiltonian vector field xt. And a flow. Here we always require it t to be from 0 to 1, and also the Hamiltonian vector field is periodic, i.e. x1 is x0. So the flow will consist of some closed orbits. We know that in ordinary differential equations, even if we have a periodic system of ordinary differential equations, it does not follow that the corresponding flow will consist only of closed orbits. But here we have say that the closed orbit exists, and we have said we need it to be non-degenerate. Here, non-degenerate means that non-degenerate means that the dh is most non-degenerate means that ht is most function. Oh no. How to say that? Yes. Non-degenerate means that the differential of the flow at time 1 should satisfy this flow condition that we must map that the differential of phi 1 must have no trivial eigenvalues. Okay, so exists, and lower bound is given by the sum of Betti numbers of x. We say this is a special case of the Lagrangian intersection theory because it is given by considering the product space as a symplectic manifold, and then the non-degenerate closed orbit corresponds to a deformation from x cross 0 to 0 from x cross a point. No, to the diagonal. For diagonal. Yes, to the diagonal. So this will be a special case of the Lagrangian intersection theory, but it seems easier to prove. In fact, in 2000, Fukaya and Ono have proved this in case x is semi-positive. Okay, so why the pseudo-homomorphic curves went into our went into the so why the Riemann-Roch theorem went into the Fourier theory? This is because in to attack Fourier theory, we firstly define uh, we apply variations, calculus of variations to the action functional A. A is a map from now we consider the Hamiltonian case, so it will be easier. It is a case will be from periodic orbit, periodic orbits. Periodic orbits to contractible periodic orbits to R to the integration of X tilde pull back the omega on the sphere. Because it is contractible, we can always contract it into a point. So we have a corresponding disk instead of the circle. So we can give an integration over this disk, and this is minus sign. It is plus sign because when we consider minus the integration of ht of what dt on s1 something maybe it is htx htx. So this is the action functional. That is in the classical mechanics. It is just the Lagrangian L. The minus of the kinetic energy minus the how to say this? The kinetic energy minus the potential energy, or the inverse. Anyway, so this is the definition of the action functional, and we apply calculus of variations, then we obtain a partial differential equation. That is dsu plus js ju times dtu and plus the gradient of htu is 0. Here ju is an almost complex structure on X. This means that it is, because that is symplectic, it always admits a almost complex structure. So we just pick one of them, and the gradient yes. So this is called the flow equation. And the solutions are periodic orbits. Solutions are orbits, are trajectories. Connecting periodic orbits. Non-degenerate. Then we obtain a moduli space of solutions. That is because it is trajectories connecting periodic orbits, we have in fact a cylinder S1 cross R to X, and the partial differential equation, the solutions to this partial differential equation is some special types of a smooth map from a cylinder to X, and this will give a moduli space M, which is a subset of the space of smooth functions, smooth maps. So then we want to determine the dimension of the moduli space, and also we need compactness. So Riemann-Roch theorem focuses on the dimension, and you will see that if we want to determine the moduli space, we first view it as an intersection of two Banach manifolds, because it is necessarily infinite dimensional. So we write it as an intersection of two Banach manifolds, and then this will tell us M is a Banach manifold of finite dimension. This is the Fredholm theory, which tells us that M must be of finite dimension, and then we have we can talk about the dimension of M. So how to compute? We just linearize the differential operator ds plus ju dt and plus gradient ht. This is of order 0, and this is of order 1, to get a linearized Cauchy-Riemann operator. And this is in fact this in type of this form. And now previously J is depending on the solution U, but now when we take a linearization, we fix the U and consider the tangent space. So J becomes almost complex structure that is independent of the solution. So it becomes a linear operator and plus some degree 0 term, order 0 term over the Riemann surface S1 cross R. And we know that once it is Fredholm, then the index, if we write it to D, the index of D will determine the space, the dimension of M, because it is the index D is the dimension of tangent space. And once we know that it is a manifold, the dimension can be seen on every tangent space. So the index of D will determine the dimension of M. So once we can compute this, we know the dimension of this of the whole moduli spaces. So Riemann-Roch will tell us the index is determined by Maslow's index. Okay, that is why the Riemann-Roch theorem goes into our proof for the unknown conjecture, or goes into the flow of theory. But we have a more elementary motivation without referring to the flow of theory. when we considering purely pseudo-homomorphic curves, we have a like in Gromov's case, 1984, we have a set of we have a modular space of pseudo-homomorphic curves, and we want to determine its dimension. That is a set of S2 to X, where X is a almost complex manifold or symplectic. And we want dimension 0 case so that we can counting curves. We can count curves. So when we count curves, the curves this will appear to be a topological invariant. And in Gromov's case, it helps him to determine if a symplectic sphere can be embedded into a symplectic cylinder. So this will lead to a non-squeezing theorem. Okay, that's all the introduction before we go formally into the Riemann-Roch theorem. Are there any questions? Okay, so if you have questions, you can also send an email to me, and that is all I want to say today. Oh, there may be some remarks. Yes, in order to compute the index of involution, because there are easy counterexamples towards the case there is no involution, and maybe there is a beautiful picture drawn by Auden. Let me find out his where. Let me find out his picture. That will give that will give an easy counterexample, so we must need the involution. Where? Wait a minute, I'm finding out this book. Okay. Okay, I think there will okay, yes, that is how to share the screen. Okay, yeah. Yes. So this is what Arnold himself considered. This will be a counterexample toward the case that there will be no no not this, but another one. There will be a easy counterexample to this. No, not here. Not here. Anyway, there will be counterexamples that is given by Givanto. So the case of non-involutive symplectic manifold will have an counterexample with a smaller lower bound. But Flower proves this in a great topological restriction. I don't quite study the case of Hamiltonian periodic orbits. Maybe there should be, but in Flower's original proof, he uses a topological restriction that that is sufficient for Arnold conjecture to hold. So he don't need the involutive condition. But if we want to drop the cohomological condition, then we must add the requirement that there exists an involution. Okay, so are there any other questions? So maybe I need to share the screen. Okay, so see you tomorrow. Oh yes, it is. Yes, we can just directly change the two coordinates. Okay.